Okay, Unit 4 deals with, how we can use derivatives to understand what an original function looks like or how it behaves. So using derivatives to better understand functions. Okay, and we will start by talking about a critical point of a function. Okay, a critical point is when a derivative of a function equals 0 or is undefined. Why are those critical points? Well, let's see what is going on at those locations. Here is a function. This is f of x. Let's look at when its derivative is 0 or is undefined. So right here, slope is 0, derivative is 0, horizontal tangent. Right here, derivative is 0. Right here, 0. Right here, sharp point, derivative is undefined. Right here, derivative 0. These are all maxes and mins of our function on intervals. They're all kind of like tops and bottoms. They're all on locations of humps of our function. These are interesting locations of our function that we are going to, deal with. Okay? So we have maxes and mins. Are there any other locations where we see a derivative that could equal 0 or undefined? For this graph. Thank you, Mr. O'Keefe. We have also this point right here where the derivative is 0. Well, we would call this a max, this a min, max, min, max, if you want to go ahead and list those off. This point right here is neither a max nor a min. Okay? So what are special about critical points? They are possible locations of maxes and mins. Okay? All maxes and mins will occur at a critical point, but not all critical points will produce a max or a min. All maxes and mins from critical points. But not all critical points produce maxes and mins. Okay, now another fancy math word for maxes and mins are extrema. Okay, fancy word for maxes and mins. There's two types of extrema. Relative extrema. Which we call local max or mins. Local max slash max. Local max or min. If you come up here, we would call this a local min and this a local min. Then there are absolute extrema, which are overall maxes and mins. Okay? Here, I would say this point looks to be a little bit higher than that point. I'd call that an absolute max. Okay, this function would not have an absolute min because it's trending towards the negative infinity in both directions. So no absolute min. Well, today we are not going to worry about absolute extrema. We're only going to worry about relative extrema. Now, we can also say the locations of absolute extrema are also relative extrema. So we're going to be focusing on relative extrema. It might happen to be the location of an absolute extrema, but we don't really care for today. Okay, but we're going to find out these locations of maxes and mins. Okay. Let's go ahead and find critical numbers for some functions. We're going to throw in a third here. How do you find a critical number? Very simple. Just when the derivative equals 0 or is undefined. I take the derivative. I set it equal to 0 or C when it's undefined. Is 12x cubed minus 12x squared ever undefined? No, it doesn't have a denominator, so I don't have to worry about it. So I can actually just, disregard that equal to undefined. And then we would just factor to solve. Okay, there. Possible locations of maxes and mins for F. Okay, do it for the other one. This should look familiar to us. We had a test question. Some of you forgot how to solve quadratics. And again, those are possible locations of max and mins. Let's look at a third location. Third function, 1 over x, if you have space for 1 over x. So I get the derivative is negative 1 over x squared, right? Does this ever equal 0? No, but it can be undefined. This is the whole, make sure we figure out when some location is 0 or undefined. When x is 0, we'd have an undefined tangent slope there. Okay? It's actually the location of a vertical asymptote, but this is like a situation where even vertical asymptotes will call critical points for the functions, critical locations. Okay? Now, great. We found possible max-min locations, but how do we know if those are maxes or mins? Which ones are they? Or are they neither? Are they situation here where you just flatten out and keep increasing? Okay, so that's what the rest of the class is going to be, finding if these critical points are locations of maxes and mins. And we are going to use derivatives and values of derivatives to help us. Okay, and let's recall, what you can write about functions by looking at slopes of secants or slopes of tangents. Okay, recall the slope of this line, this would be the average rate of change of the function between A and B. I would say from that information that on average, f of x, and since this is a positive 1/3, I'd say on average f of x is going up 1/3 of a y per x unit from A to B. Okay? Okay, so on average my function is going up. Well, that's the average rate of change, but now if we look at tangents and the slopes of tangents being the instantaneous rate of change, you can say at this exact moment, at x equals b, the function is going up 2 y's per x. That's it. So knowing that this is positive 2 is telling me my function's going up. If I looked at another location, like here, let's call this C. Knowing that this slope is negative, I don't like to do that, I'm better than that. Knowing that the slope is negative is telling me that this function is moving downwards at this moment, right? If I'm looking to left or right, my function's going down. It's going down at the rate of which that slope is equal to, okay? Let's just confirm that a little bit more. If you look at the graph of this function, and I started sketching tangent slopes everywhere, like here, 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 you know, and just started doing a bunch of them. What would I be able to see? I'd be able to see that we'd have positive tangent slopes here. We'd have a 0 tangent slope here. We'd have negative tangent slopes here. We'd have a 0 tangent slope here, and we're back to being positives here. Now, if you look at this function from left to right, how can you describe this function? This function is going up when the derivatives are positive. This function is going down from left to right when its derivatives are negative. Do we notice that? It is neither going up nor down when the derivative is 0. Okay? So, when its derivatives are positive, we are going up. We'll call this increasing. When the derivatives are negative, we are going down from left to right. We'll call that decreasing. And when we have a 0, f of x is not going up nor down. It is constant. So what we are going to do is we're going to say, okay, here's my critical point. I have a critical point here and a critical point here. But we're just going to be able to say, okay, when x is -1 and 1, I have a critical point. Then, if I know the signs of my derivative, I know what my function is going to be doing around that critical point. I'll know if my function is going up then down or down then up. And I'll be able to tell whether or not that's going to be a max or a min. Okay? Now, just in general, we will be able to say that something is increasing or going up from left to right if its derivative is positive. Something will be decreasing if its derivative is negative. Something will be constant if its derivative is 0. F will increase when f prime is positive. V will increase if V prime is positive. What if I have f prime? When will f prime increase? Discuss with your neighbors. See if you guys can come up with the answers. F prime will increase when? It's a simple answer. I just gave you a couple of examples. F will increase when f prime is positive. V will increase when v prime is positive. What about f prime? Mr. Pittman?
When f double prime is positive.
Exactly. When f double prime is positive. If I want to figure out when something is going up, just look at its derivative and see when it's positive. Now we'll talk about how do we find when something's positive or negative. Okay? Well, before we go back to this first derivative test, let me show you what we're going to be doing. Now, we're going to pretend like we don't even know what the graph of f looks like. We're going to pretend like we only have values of f prime. I'm going to create a two-dimensional number line. We will be using number lines a lot in this class, okay? Especially in this unit. And we're going to focus our attention at -1 and 1. And I'm going to analyze the signs of f prime. And by knowing the signs of f prime, I'm going to be able to talk about the behavior of f. Okay? Now, I'm going to, and I'm just going to do an analysis. I'm kind of like making this up based on the graph that I saw. But we're going to do an analysis. And we're going to be able to tell that, first, these are zeros. Okay, good. But I'm going to be able to discover that I'd have positive values here, negative values here, and positive values there. Okay, this is just something that we will be able to analyze and get. It's not just coming out of thin air. Okay? If I know f prime is positive, what is that telling me about the behavior of f? It's increasing. That's the word I'm looking for. If I know f prime values are negative, I know f is decreasing between -1 and 1. If I know f prime values are positive, we're increasing to the right of 1. It's because of this that I will be able to say, oh, f must look like this. Increasing to flat, to decreasing to flat, to increasing. And that's how I'll be able to tell, without even knowing what f looks like, that when x equals -1, I'm going to have a max. When x equals 1, I have a min. Why? Because thinking about things going from left to right, if I'm going increasing to decreasing, we're going to have a max right at that 0. If I go decreasing to increasing, boom, going to have a min. Okay, that's the first derivative test. Okay, if we look at a critical point C, okay, if I look at the signs of the derivative around the critical point C, if the signs go from negative to positive, that's telling me that f is going to decrease and increase. That is telling me that at C, I will have a min, because decreasing to increasing from left to right, you know you have to go down and up, you're going to have a min. So this is how we're going to discover if our critical point is the max or min. We'll look at the signs of the derivatives around it. Here, we have a max, but what are the signs of the first derivative doing? They're going from positives to negatives. You can see the positive tangent slopes, negative tangent slopes. That means f is going to increase and decrease from left to right, increasing to decreasing. C is going to be the location of a max. Now, if we don't change signs, Here, we'll go from positives to positives, which means I'm increasing and then increasing. Here, it is a critical point. It's when the tangent slope is vertical. That's an undefined tangent slope. F prime values are going from negatives and then negatives. These are neither maxes nor mins. Okay? Now, I have a question that I'd like you to discuss with your neighbors. Okay, if f of x only has critical points at 1 and 4. Okay, so I'm just going to go ahead and draw a number line just to denote that. So at 1 and 4, at 1 and 4, I have f prime values that are zeros. If f prime at 2 is negative, is it possible for f prime of 3 to be positive? Discuss that with your neighbors. Discuss. What do you think? Is it possible? No. I mean, maybe there's a situation where it possibly could happen, but if you go from negative values to positive values, you're going to have to cross through a 0. We were told that we only have critical points at 1 and 4. So that means I'm not going to have any undefined points. So no, if this at 2 is negative, that means all of the signs are negative. This brings us to a situation of the test point, or when are functions positive or negative? Mr. Navarro.
What is it on a sharp point going down?
Then that would be a critical point. Yes, that'd be a undefined tangent slope.
Right. Thanks.
Okay, when I ask you when is something positive or negative, okay, let's just think about a function. Here are positive values and negative values. Notice that if you find the zeros everywhere between the zeros or outside of the zeros, all of the points have the same sign. It's almost too simple to mention, but it's super important, okay? If you find the zeros of a function, the values in between or around the zeros are all going to be the same sign. All of these values in between -1 and 1 are all positive. Between 1 and 2, these are all negative values, okay? So if all the zeros are found, you only need to find one point and its value. And if that point is positive or negative, the rest of the points are going to be all positive or negative on the interval. Okay? That's the whole concept of a test point, okay? Or finding when something is positive. Find the zeros first, and then in between the zeros, you will see all positives or all negatives, okay? Here we go. Here's our first example of how we are going to determine whether F's critical points will be maxes or mins. Now, I'm first giving you F prime. So we don't know what F looks like, but we're talking about F, okay? F is some function. This is its derivative, okay? Now, by just looking at the derivative, you could tell critical information about this F, okay? The critical points. The critical points are when F prime is 0 or undefined. Okay, so I will set this, which is F prime, equal to 0. And I get 2 locations. Okay? Now, the question becomes, will those be maxes or mins or neither? This is what I will do. I will create the number line that I was talking about. I will plot those two in the correct order from smallest to largest. And above the line, I'm going to look at the signs of F prime. The below the line will tell me the behavior of F. Okay? Now, I have what F prime is equal to, and I know these are the zeros. Because I know all of the zeros, if I just look at one point, here, here, and here, and find the sign at that one location, I will know the signs of the derivative at all of the locations here, and here, and here. Okay? Now, I can write down a number, or I can just kind of think of a number. I'm just going to think of a number, so I'm going to think of a number like 4. Now I can plug in 4 into x minus 3 times x plus 2. Now the specific value is not important. It's just the sign of the value. That's important. So when I plug in 4, I get 4 minus 3, which is a positive, times 4 plus 2, which is a positive. Since at 4, we have a positive sign, all of the signs of the values of f prime will have to be positive to the right of 3. Okay, again, I'm using x minus 3 times x plus 2. This is f prime. I'm finding the signs of f prime. Okay, between -2 and 3, I'll think of 0. If I plug in 0, I'd get a negative times a positive. Negative times a positive. That tells me that at that point it's negative. Well, since I found all of the zeros, all of the points there have to be negative. If I look to the left of -2, like -3, I'd have a negative times a negative. That is a positive. Because I've analyzed the signs, I know the behavior of f. Since f prime is positive, f is increasing. Since f prime is negative, f is decreasing. Since f prime is positive, f is increasing. Now, without even knowing what the equation for f is, I know what the shape of f looks like. I know it's going to be increasing to decreasing to increasing. You don't have to be able to sketch this to know that at -2, this is the location of a max from left to right going up to down. At 3, this is the location of a min from left to right, down to up, decreasing to increasing. This is the shape of f, where this location is at -2 and this location is at 3. The y locations are not going to be important for us in this class. Okay? At least for now. They will be in the future. Okay. Your turn.
Is it our are relative to extrema.
Yeah, there's a max at -2, and there's a min at 3. At x equals -2 and x equals 3. If you're trying to find specific values, that's going to take you a while. Like plugging in 2.5 and like squaring 0.5 or cubing 1.5. That's not what we want to do. Instead, we want to focus on just the signs. Understanding when we square something that is positive or negative, or cube something that is positive or negative, how that affects the signs. And we're looking at the locations of relative extrema of f of x. Without knowing what the equation of f of x is, by looking at its derivative, I can analyze the shape of f by looking at the signs of the derivative. Okay, check your answers with a neighbor and list your critical points as maxes, mins, or neither. Make sure you go to the right of 4 as well. We got to go all the way to negative infinity and all the way to positive infinity. So make sure you get to the outsides and inside your intervals. Okay?
Is that right?
No. Don't really care about that. I just want you to plug in values to know the signs, which will tell you what f is doing. So plug in like 5. If I plug in 5, am I going to get a positive or a negative?
So this wouldn't mean like a max or min in the graph?
No,
Okay.
because this is f prime, so
yeah.
not f. That's the difference. It's squared and cubed. It disappeared on you. So that's going to change these. Okay. We have the critical points. Now we need to see the signs of f prime between our critical points. So I'm going to plug in a value, like 2.5. If I plug in 2.5 into f prime, am I going to get a positive or negative? Well, let's see. I got 2.5 minus 2. That is a positive. I got 2.5 minus 3, which is a negative. But that negative is going to be squared, so that's a positive. I have 2.5 minus 4, which is a negative, cubed, which remains a negative. So I have a positive times a negative. That means I have negative f prime values between 2 and 3, which is super valuable because it's telling me that f is decreasing on the interval between 2 and 3, where these are all zeros where we have, possible maxes or mins. Now keep doing it for the other intervals, to the left of 2, between 3 and 4, and to the right of 4. Check to the left of 2 again. Good, but at 3, you need to flatten out. See if you can get that. Okay, let me just show you here and we're going to do more of these. So if I plugged in like 0, I'd get a negative 2 times negative 3 squared times negative 4 cubed. That's a negative times a positive times a negative. You know that is a positive. That means f is increasing. Then at 3, say 3.5, I have a positive. I know this being squared is going to be a positive. 3.5 minus 4 is a negative. Negative cubed is a negative. So that is a negative. And then to the right of 4, positive, positive, positive. That is telling me that f is going to increase, then decrease, then flatten out, then decrease some more, then increase. Which means 2 has got to be the location of a max. 4 has got to be the location of a min. And 3 is neither a max nor a min. And if you want to kind of sketch the shape of f, so this is what it would look like. Increasing to decreasing to flattening out to decreasing to increasing. Something like that. All known by looking at just the signs of its derivative. Okay? Well, let me give you the graph, or give you the function of f. Let me just say, here's f. Find me the relative maxes and mins of f. Well, now you just have to do one step to the previous two problems. You need to find the critical points. You need to find f prime. You need to set it equal to 0. You need to find those critical points, plot them on a two-dimensional number line, then analyze the signs of f prime. Okay? So, this is given f, not given f prime. How to find the locations of max and mins given a function. First, find the critical points. Set the derivative, which you need to find, equal to 0 or c when it's undefined. Second, analyze the signs of f prime around the critical points. This is where you use your number line. Okay, here we go. Question. Oh, you already got it? Or no, I want to do this first one, and then you guys will do the next one. Okay, so boom. F prime. Set it equal to 0 or c when it's undefined. There's no denominator, it's not undefined. Find the critical points. Solve by factoring. Okay? Then, analyze the signs of f prime around these 2 points. Now, here's where people sometimes mess up. They're thinking, oh, I need to use x squared minus 8x plus 7 because that's f prime. Well, if I plugged in values like 8 and 5, it's going to take me a while to figure out those values, right? I don't really want values. I just want signs. I just want positives or negatives. So this adding and subtracting makes it more difficult. What we want to use is your factored form, your simplified f prime. This is a product. It is a lot quicker to find signs of function values if we have a product rather than adding and subtracting, because we can just figure out positive times a negative is a negative. Positive times a positive is a positive. So it's almost like once I've factored this, I don't even want it anymore. I don't even want to look at it. I'm not going to use it. Use this. I plug in a value like 8. 8 minus 7, 8 minus 1. Positive times a positive. Positive. Plug in a value like 5. Negative times a positive. Negative. Plug in a value like 0. Negative times a negative. I like to work from right to left. I like to work with my largest values and then work my way left for this. But know that when we're talking about the behavior of f, it's increasing from left to right until it gets to the 0, decreasing until it gets to the 7, and then increasing. So increasing until there, then decreasing and increasing. Exactly where the locations are? Well, your book will have you actually find the y-coordinate locations, so you know exactly where to put the points if you were to sketch f. I do not care about that as much. It's just going to be unnecessary work to plug in 1 here and 7 here and to figure out the y-coordinates. So don't worry about it. Just find the x-coordinates. Okay, so 1, increasing to decreasing, max. 7, decreasing to increasing, min. All right, you guys do the next one all by yourselves. Sure. Yep, very good. Good. Make sure you check between 0 and 1 as well. Factor out 4x squared. Very nice. Check your answers with a neighbor. Don't rush your neighbor, though, if they're not done yet.
Is that right?
To the left of 0 can't be just 0. It's either positives or negatives. If you found all the zeros, then to the left of 0 it's got to be either positive or negative.
Like if you plugged in, I was plugging in 0.
Good. Go ahead and check with a neighbor. Okay, again, use your simplified f prime. I think we're all doing that, hopefully, but it is going to be a lot easier to use your simplified f prime because it's a product, and since it's a product, you'll be able to figure out, you know, positives times negatives a lot quicker than just plugging in values and subtracting and stuff. Plug in 2, definitely get a positive. If I plug in 0.5, I'd have a positive times a negative. That's a negative. If If I plug in negative 0.5 though, we're going to take that value and square it, making a positive times 4 is a positive, and then negative 0.5 minus 1 is a negative, so this is a positive times a negative as well. So that means it's a negative. That means f decreases till 0, it decreases from 0 to 1, then it increases from 1 on, which means at 1, this is a situation where you have neither a max nor a min. At 1, you definitely have a min. So if you want to think about the shape of f, will be decreasing, flattening out, decreasing, increasing, something like that. Okay? Now, for practice, we can go back and find the critical points from the first two problems, but we need to continue to move on. So we're going to do this problem. It's a tricky problem. If f of x equals x cubed plus 3x squared, when is f prime increasing? About 80% of you will get this wrong. Let's see if you can get it right. Question is, given f, which is x cubed plus 3x squared, when is f prime increasing? See what we get. Anybody got it? Oh. Very nice, Miss Hathaway. No. You're very close, though. You have the right idea, but x should be -1, not 1. Nope. Nope. Very nice, Miss Wynn. Excellent. Very good. Excellent. Nope, fell into the trap. Fell into the trap, Mr. Navarro. Yeah, you got it now? Yeah. Fell in the trap. Oh, nope. You're out of the trap. How come you got this, though? And then you got that?
I'm looking at this like that.
Oh, yeah, but do it using calculus, not using your vision. Very nice. Excellent. All right, maybe not 80% of us. Okay. So here's the key. Something increases, like I told you before, when its derivative is positive. If you're asked when is f prime increasing, you need to figure out when the second derivative is positive. So you need to take the derivative and its derivative. Find out when this is positive. How do you figure out when something's positive? Find the zeros. When you find the zeros, around your zeros will all be the same, positives or negatives. There's one zero at -1. To the left of -1, I'm negative. To the right of -1, I'm positive, which means f prime goes from decreasing to increasing. F prime is increasing when x is greater than -1. This is the type of process that we need to become accustomed to find when something is going up or down and using calculus to figure it out rather than like graphing it and looking at it. I don't want you to graph and look at. Pretend you don't have calculators, okay? All right. Now, let's look at if I'm giving you the graphs of f prime. What information can we gather about f? So again, this is f prime's graph. I'm not giving you the equation of f prime, I'm just giving you the graph of f prime. And I'm asking you for what are the critical points of f. When is f, let's just talking about increasing. When is f increasing? Where does f have relative extrema? If you say I have a max at x equals -1 and a min at 2, you're wrong. This is not the graph of f. This is the graph of f prime, its derivative. Okay? So what does it tell us? Well, remember, the values of f prime tell us if f is increasing or decreasing. Okay? What I would recommend you do is go ahead and create this two-dimensional number line and evaluate the signs of f prime. Now, the signs of f prime, it's not the slopes, it's just the values. Well, f prime values are positive if you're above the x-axis, right? Or your y's are greater than 0. F prime is negative if you're below the x-axis, when your y's are less than 0. Where do we have zeros? We have a 0 at -3. We have a 0 at 1. We have a 0 at 3. My values are negative until -3. My values here are positive until 1. They are negative from 1 to 3, and they are positive after 3. That is telling you that the original function f will decrease till it gets to -3, increase from -3 to 1, decrease from 1 to 3, increase after 3. We know the critical points are the zeros. So the critical points of f are at -3, 1, and 3. When is f increasing? We would say it's increasing from -3 to 1, but not including -3 and 1, because we are not increasing at those points. We are constant at those points, which is why I have these open brackets. And then we are also increasing from 3 to an infinity. You can use these open brackets again, because that's when f prime is positive. If you'd like, you can use the inequality notation from -3 to 1, and then greater than 3. Where do I have relative extrema? Well, again, not here, but at the zeros of f prime. Those would be possible extrema of f. So -3, we go from decreasing to increasing, min. 1, increasing to decreasing, max. 3, decreasing to increasing, min. And if you wanted to, you could kind of sketch. We'll be decreasing to -3, increasing until 1, decreasing from 1 to 3, increasing after 3. Something like that. Somewhere we'll be able to figure out exactly how much we're going up or down, how much we'll be going and getting to exact points and stuff later. But for right now, that's the shape. Okay? All right, your turn. I would like you to tell me the critical points for f when f is just decreasing, and the relative extrema for f. The reason why I'm writing this repeatedly is so you know you are not given the graph of f, you are given the graph of f prime. So you need to get information from the graph of f prime to tell you about f. Check your answers with a neighbor. Very nice. Yep, very good. Check your answers with a neighbor. We should have critical points at 0 and 2. Why? If you looked at values of f prime, the signs of f prime, we see a 0 at 0. We see a 0 at 2. We'd have positive values and then negative values and positive values, which is telling me f is increasing to decreasing to increasing. So when it's f decreasing, just from 0 to 2, not including 0 and 2, because we're constant at 0 and we're constant at 2. Where we have extrema at 0, we will have a max, and at 2, we will have a min. So you can see f would look like this, increasing to decreasing to increasing. Okay? Kind of should make sense, right? If this is an x squared, we knew that the original function f is probably a cubed, right? Using the power rule, a cubed function's derivative is a squared function. Does that make sense? All right. Really quickly, do this one. For what x does f of x have a relative min? For what x is f of x increasing? Look up to see if your answers are correct. Questions? All right. Moving on. If we have time, we'll come back to using a calculator to find solutions and stuff like that. But we're going to, as we get later and later in the year, we use them more and more. Okay, but not for a while. 6 tests, maybe we have a calculator part on the sixth test. Maybe the 5th. We'll find out. All right. The mean value theorem is the second of 3 theorems that you need to know in BC calculus. Okay. Mean value theorem deals with differentiable functions. Okay. So given a differentiable function, Now, what does it mean to be differentiable? It's very important to understand what it means to be differentiable. Anybody? You can find the tangent slopes, which means you have to be continuous and without any sharp points. Excellent. Continuous without sharp points. If you are told the function is differentiable, automatically means it's continuous. So that's good. Okay, so given a differentiable function f of x on an interval a and b, there must, so on an interval, so it just has to be differentiable on an interval from a to b. There must exist an x, at least one x between a and b, such that the derivative at that x value is equal to the slope of the secant created by the 2 points. Given a differentiable function f of x on the interval from a to b, there must be some x between a and b such that the tangent slope at that value is equal to the secant slope connecting a and b. Okay? Let me show you how that looks. Just plot 2 points anywhere on this little graph. Anywhere. Okay? As long as they're not like on top of each other, then that would be bad. It'd be a non-function. Now, I'd like you to connect those 2 points in any way, so long as there's no discontinuities or sharp points. Don't use a straight line though, that's kind of defeats the purpose. I'm just going to connect them like that. I'd like you to sketch a secant line between your 2 points and kind of be able to visually see the slope of this secant line. I guarantee you there's a location on your graph that you will be able to sketch a tangent line the exact same slope of that secant line. Those lines would therefore be parallel to each other if you looked at them on the graph. I can go ahead and just plop one right about here. And I see that my tangent slope equals my secant slope. Okay? Did it work out for everybody? Some of you probably have multiple locations, right? The mean value theorem just says there's at least one. There might be 5. Okay? Rolle's theorem is just goes on top of the mean value theorem. Rolle's theorem is like the same as the mean value theorem, except these points are equal to each other. If your points have the same y values, what does your tangent slope have to be equal to? 0. Very nice. 0. No matter how I connect them, we'll have to have at least one location where my tangent slope equals that secant slope. Okay? Let's go to the last problem, where it's given you a graph. They say, given the graph of f, approximate the locations of f of x guaranteed by the mean value theorem on the interval from -6 to 4. Okay, it's very important that the interval that they give you is what you pay attention to. We're looking at the secant slope of this interval. So 1, 2, 3, 4, 5, 6, -6 to 1, 2, 3, 4 to 4. Okay? Well, understand what your secant slope looks like. Then sketch the locations where your tangent slope is equal to that secant slope. You'd say at approximately 1, 2, 3, 4, approximately -4 and like 2.5. Okay? We can do that with functions. Show that this follows the mean value theorem from -2 to 2. First thing I need to confirm is this is differentiable. Why? It's continuous, I know for sure. How do I know it's not any sharp points? Well, typically if you have fractional powers, or like sometimes with some square roots, so fractional powers and square root, you'll see sharp points. Okay, this has no fractional powers, so we are differentiable. All I need to do is find my secant slope. My secant slope will be off of the points -2, which ends up giving me 8, and 2, which ends up giving me 8. I then find the secant slope using my slope formula. And I get 0. I need to see when my tangent slope, I don't know what just happened. I need to see when my tangent slope equals that secant slope. There we go. Okay, f prime in this case is 4x cubed minus 4x. I set that equal to 0. 4x times x squared minus 1. I can be factored to 4x, x plus 1, x minus 1. I get 3 locations, -1, 0, and 1, all between -2 and 2, that at least I knew 1 was guaranteed. I found 3. We'll do the rest of the examples, except for the calculator examples. We'll get to the calculator stuff at a later point in time on the video. Okay, let's do the other mean value theorem problems. So we're looking at x squared, the interval from -2 to 1. We want to find what value is guaranteed by the mean value theorem. I'd like to just look at this because we understand what x squared looks like. From -2, it'll be up at 4 to 1. So we have this negative secant slope. It looks like I need to have a position right there. Okay, let's figure out what that position is equal to. So first I find my secant slope. I get 4 and 1 as my y-coordinates. So 4 minus 1 over -2 minus 1 gives me 3 over -3, which is -1. I'll set that secant slope equal to my tangent slopes to figure out the x-coordinate. That's set equal to 2x. That equals, x equals -1/2. So x equals -1/2. If you go back to the graph, you can see this x-coordinate would be -1/2 that produces that. Just like we saw, which is cool. Okay. Sine from 0 to pi. Let's find my secant slope. Zero, 0, and pi 0. So my slope is 0. The derivative is cosine. When is cosine equal to 0? Well, pi over 2 is the value that is between 0 and pi. This is Rolle's theorem. This is the mean value theorem. And that's our lesson.